Hello, my name is Ijeoma Ebhogiaye. I'm the DFT lead at Veriest. Today we're going to talk about design for test consideration for automotive designs. I'll tell you a little bit about Veriest. Veriest is a semiconductor services company with approximately 150 professionals. It's with headquarters in Israel. Veriest has got design centers in Israel, Serbia, Hungary, and UK. The UK site was opened early this year, and the UK site is made up of very strong engineers, highly experienced, with expertise in physical design and DFT. Showing on the screen now, it's some of the physical design and DFT capabilities. Going further to our topic for today, here's an introduction. These days, we hear design for test concepts for automotive devices being regularly discussed within the industry. With the advancement of automotive design, DFT can be appreciated for what it is. DFT is not an afterthought or mundane design task. DFT is a chip design facet that is evolving with innovation and interesting challenges that arise alongside. The scope of this presentation is on DFT consideration for executing automotive projects, making sure that the design meets the appropriate automotive safety integrity level within the ISO 26262 functional safety standard. Going on from there, why DFT consideration for automotive projects? I've put this in 3 facets. First one, safety and reliability. Automotive products have always been about safety and reliability. Manufacturing testing was never a major issue, and there was no need to push for leading edge technology. Automotive industry always relied on mature technology nodes with already proven and established reliability. However, due to increase in demand for automotive chips, new players are entering this market, many of whom have never focused on safety and reliability. The next facet is inadequate fault models. Traditionally, DFT engineers have always pushed for DFT considerations to start at project conception. With automotive, this requirement has pushed even further upstream to system level. DFT, as we know, is about manufacturing defects and shipping products with extremely low defective parts per million, DPPM. Automotive brings additional requirements of safety and reliability, which involves in-system tests. Therefore, known fault models are not enough. Even using more powerful fault models, such as cell-aware or timing-aware, are inadequate. This led to the prominence of logic-based test technology. The next facet to look at is design complexity. The complexity of automotive products drives DFT activity to what is known today as shift left, which is more or less everything in RTL. The reuse of blocks not designed for automotive products does not facilitate this move. Moreover, project timescales are usually not flexible enough to accommodate changes without impact on other facets of the design flow, such as physical design. Careful consideration of aspects of DFT methodologies are needed to maintain high coverage, aiming for low DPPM, and still allowing for the ability for in-system tests. Now, what is logic-based? Let me explain a little bit about what logic-based is. L-based is a technique that is implemented in the design to enable in-system self-test. It enables the design to be tested autonomously in field without external data. LBIS logic is inserted with an EDA tool. It adheres to functional safety requirements that meets ISO 26262 standard for automotive semiconductor industry. Scan chains already implemented for manufacturing tests are reused for LBIS. Seed and expected signature values can be hard-coded or programmable. LBIS operation are specified at system level. For example, estimated LBIS run cycle time, shutdown time, or functionality while LBIS is in operation, percentage cumulative test coverage. To consider DFT for implementation, here is an example design. Example design specification for DFT consideration. In this specification, it's a SOC design with multiple macro blocks, say 8 macros, multiple power domain, multiple clock domain. Hierarchical DFT implementation, all macros wrapped with DFT core wrappers, embedded IPs with embedded scan chains. The design we said 8 macros, 6 out of 8 macros will support LBIS self-test. 2 macros will not support LBIS due to functional requirements, e.g. this block cannot be in shutdown for LBIS operation. LBIS will operate at half of the highest clock frequency. 3 macros will have LBIS implemented on certain hierarchies. Some registers will be excluded from LBIS tests. Memories will be excluded from LBIS tests. Target ATBT coverage, stock out 99%. Transition fault, 92%. LBIS cumulative coverage, 70%. Achieved with fewer patterns and minimum number of seats. Estimated LBIS runtime, 30 to 50 microseconds. How frequent LBIS will run will be considered or decided at system level and should not impact DFT implementation. So that was our example. Now, what do we do here, given that DFT, in order to implement DFT, there are extra things we need to think about, extra thoughts with DFT implementation. Think about chief design overhead. Here we think there might be area overhead, there might be congestion, time and power overhead, seed and computation, so signature computation overhead. How do we mitigate this? Mitigate with design, coding style, implementation flow, sharing of test structures, reuse of functional flops for text points. So we can mitigate area overhead with those. How about congestion and time and power overhead? We can mitigate those as well by using physical data. We can apply physical data. For instance, the reuse of physical aware test point instruction strategy. Again, with seed and signature computation, there are tools out there which allows for fast computation with minimum area overhead. The next thing to consider here is DFT structures. We need to think, we are going to insert DFT structures. We need to make sure of optimal implementation and verification of these structures. Do we implement them in RTL? Do we implement them in netlist? Okay, these are the structures we are talking about here. You can see them being displayed. DFT structures, LBIS logic, on-chip clock circuitries, core wrap logic, compression logic, test points, memory-based wrappers, LBIS flow with programmable values. Here we think, are we going to use already DFT inserted IEEE 1500 logic? We can insert IEEE 1500 logic just for LBIS. On the other hand, we can connect self-test signals to functional registers. Another thing that is very vital here is the length of LBIS scan chains. This can impact the duration of LBIS run cycle time. So scan chain length must be architected carefully, considering the same chains will be used for manufacturing tests, and also making sure that compression threshold must not be exceeded. Now, here are LB-centric considerations. So in these considerations, we are looking at implementing LBs, clock propagation through OCCs with multiple clock inputs, functional clock, ATE clock, and LB's clock. Back to our scenario example, which which we presented in slide 9. That the requirements then it says that the LB's clock will run at half the frequency of functional clock. So here we have 3 clocks: the functional clock, ATE clock, which is the test clock, and then the LB's clock. We need to be able to have a clock strategy that will accommodate 3 clocks going into the OCCs. Regular OCCs usually will have 2 clock, functional clock and ATE clock, but now we're faced with a 3rd clock. So we have to architect it in a way that our shifts and capture frequencies are not impacted, and we don't have block scanchers downstream. Another thing is during LBs, clocks should not propagate to logic, which are excluded from LBits operation. We did say in the example that not all logic will have LBits. So those without LBits, we do not want clocks to propagate to those logic during LBits. That leads us to LB's clock only should propagate during LBs. So when we are running LBs, it's only the LB's clock should propagate. So we make sure during implementation that this is being accounted for. And again, it will be checked by STA. Usually STA will check for functional mode and test mode, but now we have another mode for STA. STA is standard static time analysis, static timing analysis. Will check for another mode, LB's mode. So we have to allow this in the implementation. Then memory write enable. Memory write enable ports must be blocked during LBs to avoid context corruption. In our example design, we will have memories, single port, dual ports. So, and we want, as soon as functionality is resumed after running LBs, when we come out of shutdown, that the memory's content are not corrupted. So we have to find a way to block the memories. The next one is X propagation from registers or hierarchies which are not part of LB scan chains. So we need to make sure that X's do not propagate. So this can be blocked with test points. Precautions must also be taken when inserting test points, especially on clock lines, so that we don't have problem downstream of the design flow. We may have problems with CTS if this is not done properly. CTS, clock tree CTSs. So we have all this. When we're implementing DFT, we need to make sure that all these precautions are taken. Another important precaution is to ensure that there are mechanisms to reset flops with no reset pins prior to running LBs. So we're going back to libraries here. Do we have flops in the libraries without reset pins? If we do, we may set them as don't use, so they will not be used. But where they are used, we need to make sure there are mechanisms to reset them prior to running LBs. Now, cumulative test coverage. So we have to carefully consider this. In our example, the requirement there is to have 70% cumulative coverage. With 70% cumulative coverage, what would this give us? How do we achieve this 70% cumulative coverage? We can do this by test points. We can do this by inserting test points. We can also do this by having plausibilities on our LB's runtime cycle. How long will the device be shut down, the functionality shut down? How long will that be? That can be increased as well, so that we have the time to run more patterns. How about running more patterns and also multiple seeds? Do we have enough time to run more patterns and run multiple seeds? Here's an example. Let's carefully look at this example. We could see here, I've put one seat with 128 patterns, giving us 65.39%. Two seats with 64 patterns, giving us 66.14%. Four seats with 32 patterns, giving us 67.17%. 16 patterns, 47%, with accumulating to two seats, the accumulative coverage 55.87. Three seats, 59.88. Four seats. So we could see if we are running 16 patterns, by the time we get to 10 seats, we have 70.34. So it's accumulative. That's what the table is showing here. But what we can see is also that in this example here, so when we run 128 patterns, we are getting 65.39%. We run two seats of 64 patterns within the same time because we're still running the same number of patterns, but two seats. And that's what the coverage is, 66.14. We run four seats, we're having the same number of patterns because 32 patterns four times, 128, but the coverage is up. Yeah, so you can study this table. You could find out that the coverage is up. This goes to show that we can achieve better cumulative coverage with shorter patterns and multiple seeds. We can achieve that with shorter patterns and multiple seeds, so long as we are running within our L-based run cycle time, which is specified at the beginning of the project. This is given to us, this is a requirement. So we have to work in order to be able to make sure that we meet that cumulative requirement. This also goes back to how we architect our scan chains, making sure that our scan chains are short enough, not too long. So in order to meet, so it's very, very crucial that we meet our time, our cumulative test coverage. And these are the scenarios of how to meet that. Conclusion. This presentation has highlighted that DFT is an integral part of chip design execution and why careful consideration must be taken when undertaking automotive projects. During DFT design process, it's important to consider all aspects of chip design flow. We saw in the scenario, we looked at architectural specification, you think about DFT. RTL implementation, you think about DFT. Verification, you think about DFT. Layout, you think about DFT. So DFT must be considered all through the design process in order to achieve high quality design and meet schedule. Basically, for automotive projects, it is vital to start DFT process early in the design phase. Failing to do this can lead to suboptimal performance. Failing to do this. Thank you.